All right, here is another example for class 19, mass moment of inertia. It's actually two examples in one because I'm going to find the mass moment of inertia of this. I don't even know what to call this thing. It's sort of a cone, but it's actually got sides that follow y squared equals to x. I'm going to do it two different ways. We're going to use hollow cylinders and rings, or discs, I should say. They're not rings. Okay, so this is actually kind of using rings. They could call them cylinders here. So what that means is we're going to break this thing up into, let's see, try to draw a good sketch of this, into hollow cylinders. All right, so it's going to be kind of like that right there. And here's some dashed lines. I should probably have drawn these with dashed lines. So you get the idea. These are going to be concentric inside each other. Maybe I'll draw another one in there. They're going to be very, like very thin though, right here. So I've drawn it like a lot thicker than it actually would be. So let's see. I'll draw the little circle in there and a little circle in there. I don't know what was that noise was for. Okay. Hopefully you get the idea. And let me start over actually, because what this the cylinder actually would be kind of like go halfway. You know, it'd be like overlapped right in there. All right, these are, again, really, really thin, the walls of this. All right, so you get the idea. And so dimensions of this, okay, well, let's just, we start out by saying dm. An incremental mass of one of these things right here is going to be the density times the incremental volume. All right, and so that volume is going to be the circumference times the thickness times the height. Right, it's where here is the height, and we're going to get the circumference and then multiply by thickness. The idea being that, like, if you had a circumference of something, and as long as the thickness of it is really thin right here, the circumference of the center, I'm drawing right here, in between the two, times the thickness would equal the area. But it would but because it's so small, that approximation will be okay. So you take 2 pi let's see, this is in the x direction. Okay, so the radius of this thing is going to equal x, right? So the radius of any of these hollow cylinders is x. And the height of this thing, right, this h right here, is, first off, we'll just call it this h, right? And then dx is what we're taking here. Another way, okay, so maybe I should also, there's two different ways to think of this. All right, one is we take their circumference right here and multiply it by, okay, we have this circumference. I'm sorry, I'm messing this whole thing up. Maybe I should start over again. And we're sweeping an area, all right? So that area would look like this right here. That cross-sectional area, and we sweep it around by this circumference right here. So this can be thought of as that area that I've shown right here. And here is the circumference. And with those two, that's going to be dV, right? So you could see that the incremental size of this thing right here. So here is the dx, is the dimension of that area, and then 2 pi x is the circumference that it's swept around. And we can replace that h, if you take a look at that, with, it would be 1 minus y, right? So the y position that corresponds to any particular x would be the height of the thing, right? Yes, yeah, okay, so it goes from 1 right here, so the height h is going to, like, from right to there, right? So this is the value of y at a particular point. Let me use this one over here. For, like, this x and y right here, here is what y is going to equal. So here would be the height right here. And so the height is 1 minus y, which is equal to 1 minus the square root of x. Okay, this is the thought process. So we could substitute that in and say that dm, an incremental mass, is going to be pi times rho times 2 pi times x times 1 minus square root of x dx. Move some stuff around. Rho 2 pi is going to be x minus x 3/2 dx. Right? All I've done is just some algebra right there. Now I take my moment of inertia equation is going to be r squared dm. And in this case, r is equal to x as the way it's drawn. So, and this will actually be, we're going to do it about y is what we're going to find. It's actually going to be about the center of mass here. So we're going to integrate that from 0 to 1, right here, from 0 to 1 of the integral of x squared, right? So that's, and then put in the dm in that place right there. So that's going to be pi. Well, I keep saying pi, but that's I don't know why. Rho 2 pi x minus x 3/2 dx, and we integrate that. Well, first what I did is I did a little housekeeping here. Bring these guys, these are constants, they're out to the side. I go 0 to 1, and that x squared distributed across those x's, I get, that was a really big one, 7/2 dx. And if I find the integral of that, it's x to the 4th divided by 4 minus 2/9 x to the 9/2, and take it from 0 to 1. I do that, I get 2 pi rho 9/32, right? 9/36. 9/36, okay. 9/36, right in here, minus 8/36. And that ends up being, let's see, double check what that is. Okay, so we put 1 into there, right? Yeah, okay, so 1 in there is 1/4, and 1/4 is 9/36. So I just got the common denominator, or the least common denominator, right? There's this other one right here. When I put 1 into there, I got 2/9. So to add 1/4 and 2/9, I multiply one side by 4 and the other side by that works, doesn't it? Sure. I think so. Okay, we get pi rho over 18. Exciting, I know. But really it's just a demonstration of the thought process. The most important part being that we want to find this thing in terms, we want to find what the incremental mass is going to be, and then we want to turn it into something that we can integrate across here. A different way to approach this, another one, is to take a disk, right, or to break this down into a bunch of disks. And so a disk would look like this right here, and we're going to go ahead and say that we already know that the increment, that each disk is going to be 1/2 r squared dm for an individual disk. And now what we could do is we could add them together. When we integrate, that's what integrating is, right? It's adding things together. So the thickness of the disk is going to be dy, right? The incremental thickness. The radius of each disk is going to be equal to x. So r is going to be equal to x inside this thing up above. And so the incremental mass is going to be rho d incremental velocity volume. Sorry. So, and we know that a volume of a disk is going to be pi r squared dy, right? So that's pi r squared is the area of this disk, and the volume is dy. So, and we know that an incremental di, an integration of an incremental di is going to be I, and it's going to be the integral of 1/2 r squared dm. We happen to know that x is equal to r, but x is also equal to y squared, right? So if we say we'll have 1/2, substitute r squared in for right here, and we have y fourthed, right? And then for our incremental dm right up above, and we're going to do it again over here, right? So we're going to say that it's going to be pi y fourthed again, right? Because that's r squared up in here, and then we're going to have dy. And I don't know why I put braces in there, brackets in there. There's no need for it. So we're going to do that from 0 to 1 again, because actually y extends to 1 right up in here. So if we take the integral of that, we end up, we'll move the stuff that's constants to the outside and integrate y to the 8 dy. We end up with 1/2 pi rho 1/9 y to the 9. We end up doing it from 0 to 1. We play around there, and we get pi rho divided by 18, which is the same answer that we got up above, right? So this is just a demonstration of the method of to use integration to get the mass moment of inertia. Frankly, most of the time we end up using by parts and using for individual tables. But like if you want to know where did we get these solutions right here, or like we could find it for the cone, maybe would be one way that we might find it for a sphere, or if we wanted to do this half cylinder right here, and we wanted to confirm that these equations were for that this is the method. I got to go through all this to get down to these other slide. We would go through this method to get to those. So it's a good thing to know how to do, or it's a good thing to recognize where this stuff, the answers in the tables come from. So that wasn't the best of videos, but it was a video. And how long did that make it, though? It was only 14 minutes. Only 14 minutes.